Like today, I will start from the radiative transfer, and in this section we will go through the two main processes which happens in the nature. The first is being like emission and the absorption, and then we will discuss like how the energy transfer will affect with this two main like kind of processes in the nature. So like if radiation or the like empty space in the vacuum specific intensity, but yeah, like if radiation will go through the medium, just like maybe any kind of gas or liquid. So the intensity will affect, and it will the effect in the intensity will depend what kind of process is being. So the first is I would like to tell about the emission. The emission is being like if if radiation is going through let's say about any of the volume element, let's take its dV. So if radiation is going through that volume element, so it the resultant radiation, resultant intensity of that radiation will be exceed. So which will be depends on the increase in like energy of that radiation would depend on the volume element, it's obvious, and the solid uh, um, in the solid angle which is extended over the radiation, and of course it would be the time, time slab. So the what here I'm trying to say is like when like radiation is going through the medium, and when there is like emission process is going on, so the change in energy of that radiation will would be proportional to the volume element, the solid angle, and then it would be the time. So here the proportionality constant which will we will be get, it can be defined as the emission coefficient, and for a monochromatic emission we can define it as a j mu. So here J mu will depend on, obviously, like it will depends on if you can say like location where the emission is going on, in the direction, time, and obviously in the like bandwidth of that radiation. So if we are studying about, if we are talking about an isotropic or isotropic environment where like radiation is emitting in all direction isotropically, like in the similar way, so we can say like j mu, which is like emission coefficient, will be the power per unit volume on that particular volume element over 4 pi. So Professor, after that, actually, I was missing something from this portion. So, like, could you like explain this thing again? Hello.
Hello, can you repeat?
Yes, yes. Actually, like, I got this expression when I was studying. So I got this. I understood this, and like after when I was getting this here, so I was a bit confused while like equating the summary from your book, that is here, from here, and like from here. So like I was a bit confused about about here. So would you like explain it?
So, Nitya, I think there is a problem with the microphone. I can hear most of what you say, but sometimes it breaks out. I think it's okay when you really have your microphone very close.
Okay.
But and I think that you are saying that there is a difference in notation or in vocabulary when comparing my lecture summary with the textbook. Is that what you're saying?
Actually, when I was comparing your like your books element and here, so I was a bit confusing, like how to from this equation, how will we get this and all this element like like here the emittivity and radio density, and like I was confused about this section and that section. And
Ah,
obviously at the last we are getting the same equation at the last, but here the things are confusing because we are going through like all we are going through like two different like processes for getting the single equation. So I was a bit confused about this like emission section especially.
yes. I mean, I in my summary, I tried to connect the equation 117 here in the textbook with equation 119. So 117 with 119 are not so obviously connected. I think you need to go through the definition of specific intensity. And that is what I tried to do in my summary. I tried to explain that step, okay? I don't know if it's super clear. It might be maybe a better way to explain it, but in order to connect with a specific intensity, we have to relate the specific intensity with dE. And we have to explain, that the specific intensity is exactly the energy that's going through a solid angle through and in that direction and within a time span dt and a frequency range d nu. Okay, so basically when you compare 117 with the definition of specific intensity, then you get equation 119. Okay, so that is what I was trying to do.
I from what I understood on the book, to go from equation 116 to 117, you use the relation 118. So so the epsilon nu rho is a, and j nu is a quality, is a quantity that depends on the medium. So J is the emissivity, emission coefficient, which is a quality of the medium, and then the mass density and the energy emitted and the epsilon is also a quality of the medium. So the relation between these two is 118, and they use it on equation 117. Get that number.
Yeah. Actually, I had got this point like from where we get. Actually, we started from here and we get the here, but I was like not getting why we are including this like so yeah, it is clear. Like thank you, Felipe. Now it is yeah clear for me. So okay, so it is fine for me now. Yeah. So can I proceed?
Yes, it's okay, Nitya. I just wanted to say, Felipe, that that's correct. I mean, epsilon nu and j nu depend on the medium, and there are different ways to describe the power emitted per unit volume. So it depends on the context. Sometimes people use different notations. Bear in mind, people mean emission coefficient, emissivity, or its notation changes, so you have to be careful from the context. But
Yeah,
yes,
yeah, yeah, sure.
Nitya, please go ahead. If you, is it okay for you to continue a little bit more?
Yes, yes. I want to like start with absorption now.
Okay, please go ahead.
Yeah, yeah. Okay. So the second main process in the universe is the absorption. So like if we take the radiation is going through a volume element with a absorption environment. So like the change in the intensity of that radiation will uh, will be the proportional to the intensity obviously and the distance through which the radiation will travel, and that is here the ds. So if we because here the radiation intensity will be loose, so here that's why here the minus term came. And alpha nu can be alpha nu will be the proportionality constant, and it will take as absorption coefficient. So now the thing is that like when in our absorption medium, which is volume element dv, if we will be having highest numbers of absorbent, I can say like highest numbers of absorbent, so absorption will be like if the higher number of absorbent, so absorption will be high. If the lower numbers of absorption, so it is obvious that like it will be it will be low absorption. So here this concept we can use, and we can define the number of objects if the number of absorption in the medium is n. So from the volume element we can say that the number of absorption element in this medium would be the n DADS. DADS here is the like volume element. Um, and it will also depend on the cross section of each like each element, each absorber element. So here rho nu will also come. So here the right hand side of this equation is actually the intensity, specific intensity definition. Here I nu is the specific intensity of a particular wavelength. N is the number of absorbers. Sigma nu is the cross section area of each absorbent. If the cross section area will be high, so it's like the if we have like if the size of bucket is greater, so like greater amount of like radiation will be absorbed. So it is the same. It's just kind of same thing. DADS is the yes, professor.
Nitya, just wanted to point out here that if you notice, this equation you're discussing now is very similar to the explanation I provided in my summary for the emission coefficient. Yes, so you don't need to pull it up. I just want to mention it. It's the same really. I do not know why the textbook did not mention this connection in the context of the emission coefficient. But I think I just wanted to point out that we see the same basically. Except that this is coming out of the beam. Yeah. I'm sorry to have interrupted. Please continue.
No problem. Okay. So the right hand side of equation is the like the specific intensity with the number of absorbent and treating with all them, and the left hand side is the is the loss in the specific intensity, the how much the loss in the specific intensity along the volume element. So like if we treat this equation, we will get this: the I nu is equals to minus of n sigma nu I nu and ds. So from if we equate this equation from 1.20, we will get the final equation, which is our absorption coefficient alpha nu, which would be the n, which would be equal to the n uh, n n times rho nu. So here n is the number density of the absorbent in that medium, in that volume in the volume element, and the sigma nu is the cross section of that element. So we can also write this equation as in terms of mass density of that particular volume element with the mass absorption coefficient, which is the kappa rho. And the kappa rho is also like also can be treated as the opacity coefficient, like the how much medium is efficient for the absorption and all the things. So from um, here we can conclude which are the most important thing is that like the validity of those validity of that equation, which will depends on few things, just like the distance between the interparticle distance should be greater from the like cross section area of each of the absorption, which is which is defined by this. But Professor, here I have one more doubt.
Mhm.
This is fine, that definition is fine, but here I was stuck with it is in this like equation, that is okay, this is fine, like that sigma rho to the power half should be the less than d. But my question is that from where this significant quantity has come, like sigma nu to the power 1/2 should be like what's the physical like mean of that?
I think, Nitya, that is the square root of the cross section is like the
Mhm.
square root of pi a squared. I mean, imagine that a is the radius of the particles. Imagine that the particles are approximated by spheres whose cross
Mhm.
section is like a disk with a radius a. So the linear scale of the cross section will be
Mhm.
proportional to the square root of the cross section. So a
Okay.
square root of sigma nu is just the linear scale, so like the radius or the diameter are of the targets.
Okay.
Y-
Okay, I understood. Yeah.
Yeah.
Mhm. Okay. And the second important thing should be know, we should be know, like the absorbers are independent. They should be independent, and they are randomly distributed over the volume element. So here these are the two main important things we should keep in mind. Yeah. So
Mhm.
yeah, Professor, like for now, I will stop here.
Okay, that's fine. Thanks very much, Nitya. So
I have a question before we continue to the radiative transfer equation.
okay, Felipe.
So in that same paragraph, they say something about absorption, true absorption, stimulated emission, and something like stimulated emission and what's the other? And natural emission or spontaneous emission. So but they don't say what's the difference between spontaneous emission and stimulated emission. When does stimulated emission happens is my question.
Aha.
Like, can I answer?
Yes, please, if you know.
Go
I,
ahead.
Yes,
I really
actually,
don't know.
spontaneous emission is like when the atom is in like higher energy state, and it will spontaneously, like it will by self, it will like remove one atom and will come into the ground state. So it will like the spontaneous emission. And the second thing is that when atom is already in higher energy state, so what we will do, we will hit the external photon to that atom, and then atom will lose one photon. That one it will lose one photon and will come to the like lower energy state. So in this case, it will lose two photon, the one which is being like heated externally to that atom, and the one when it will itself it will emit its own photon when it will come into the like ground state. So actually the stimulated emission happens in the lasers. So am I right, Professor?
That's perfectly correct, Nitya. Actually,
So there's the stimulated emission is because a photon goes into the atom, and then and the first photon, the incoming photon stimulates the atom, so the atom is emits a different photon, and then there's two photons emitted, and that is stimulated emission.
yes, that is exactly it. You have an incident photon that interacts with a target, an atom or a molecule, and this incident photon is not absorbed. It goes on, it passes through, but in passing, it perturbs the target, which emits another photon. So the impact of the collision between the photon and the molecule is to produce yet another photon at the expense of the molecule's energy. So this happens when the molecule is found in an excited state. It is mentioned here a bit in advance of what we'll be looking at next week, which is the line radiative transfer. This is what we're looking at now is a generic description of a radiative transfer, where we are not considering whether the target is a line or is it dust grain, a molecule or a dust grain. But in the case of bound systems like atom and molecules that have radiative transitions, the radiative transfer equation can be connected with the Einstein coefficients, which describe the stimulated emission. So just to summarize here, it is the stimulated emission is mentioned just to explain that sometimes this absorption coefficient can be negative. And sometimes instead of leading to absorption out of the incident radiation, it can also enhance the incident radiation. And that is called amplification. When it occurs in visible light, it's called laser amplification. When it occurs in the radio frequencies, it's called maser amplification. Maser is very commonly observed in astrophysics. Lasers sometimes in the context of active galactic nuclei. Okay, but we'll come back to that. Right now, if you want, Nitya, you can stop sharing screen and I can take over.
Okay.
Thank you, Nitya.
Yes, thank you very much, Nitya. Can I ask something, Nitya? What PDF reader are you using? I really liked it.
I'm sorry, Professor.
I was asking if you could tell us which PDF reader you're using, because I thought it was really nice. I mean, the layout, which one is it?
Actually, this is like Explorer.
Oh, I see. It's in Windows. No, I don't use Windows. So there's no way I can use it.
Okay. Yeah.
Okay. So let me. Oops. Then just organize a little bit my screen here. So this is. Okay. And right, yes. This is what I want. Okay. just want to look at this, basically the same we've just seen, but I'll be adding a new element, one that is not considered in the textbook. Strangely enough, I mean, Rybik and Leitman discuss it, but in a very restricted way, and that is an aspect that has developed a lot since Rybik and Leitman was written. I mean, of course, the book is fairly old. I can't remember where it's from, and let's check. When is the first edition here? It must be 1979. So this is an old book. Okay, so the first version of the Rybik-Leitman book was in the 80s. Okay, 1979, and since then, of course, astrophysics has progressed, and the role of scattering is become much more important, and so that is a topic we need to include now. So last time I explained more or less this idea that the variation of specific intensity in space-time includes sources and sinks. So we'll not be considering the time variation, we're only looking at the variation in space. And this fancy notation here, k dot gradient of I, is just to say the partial derivative of I in the direction of propagation of k. So we need to quantify the sources and the sinks. So the emission we've just looked at, thanks to Nitya, and we looked at this summary also last week. If this is still not clear, next time just contact me and we can discuss it again, okay? But I'll assume it's okay now. So we are describing the emission with equation 16, the variation of I nu, d I nu, difference of I nu in 2 points in the direction of array, which are separated by a distance ds, then this variation is given by the emission coefficient times the length, the separation between the 2 points. So this is the conclusion of how, this is in conclusion how we'll be describing the emission coefficient, okay? Then in turn we have absorption, and absorption leads to a decrease in the specific intensity given by this absorption coefficient. And the absorption coefficient is related to the properties of the medium, as Felipe pointed out at the beginning, through physical conditions like the density and properties of the targets, like there's a cross section. Okay. Now we're talking about something new, which is scattering. So scattering is the reflection of photons rather than the absorption of photons. Okay. So the idea here is that we have the decrease in specific intensity, but not due to a real absorption. Meaning that energy that's being absorbed by the target. So, like imagine that the grain is absorbing starlight, and as it does so, it becomes hotter, right? Actually, you must have seen this argument, and now you want to calculate the equilibrium temperature of a dust grain that's being illuminated by a star. Well, we'll look at that anyway, but the idea is that real absorption leads to an increase in internal energy of the target. But here we're talking about something different. What happens if instead of absorbing the incident photons, the targets actually reflect them? So they just reflected away from the ray. Okay, so we have this situation where we so we have oops, that's not what I want. So we have a photon, okay, that's carrying energy, that's hitting a grain, we know that's a dust grain, and then instead of absorbing, the photon is reflected, okay, and with no net difference in energy. So this is elastic scattering, and the photon is simply bounced off the dust grain, okay? So that's what we mean by scattering, okay? So that would be okay. So the difference with absorption is that the H nu is just absorbed in the medium, in the target. Okay, that would be the difference. So we will be describing absorption much the same way as we did real absorption. We'll be describing scattering much in the same way as we did for the real absorption, with the same argument. I mean, because all in all, we're talking about a decrease in specific intensity due to interaction with targets, so we can parameterize the phenomenon much in the same way. It doesn't really matter to us at this stage here to describe the specific intensity along the ray, whether the photon is absorbed by the medium or is reflected. I mean, in terms of the parameterization is the same, right? The more photons hit, the more will be reflected out of the beam. You know, so that's why we need to make it proportional to the incident in specific intensity. And in turns, we need to also have a coefficient describing the interaction with matter, which is the alpha scattering. Okay. So that is easy to see. This is how we'll be deflecting photons out of the direction I mean, like, let me draw this more clearly here. We have, this is the direction of propagation here. Okay, so that would be K. So we're looking at how the specific intensity decreases due to scattering away from the direction of propagation. Okay, I suppose this is clear for all, and you know, it's easy to see that we'll be describing this absorption exactly the same way as real absorption, because we're removing photons from the beam, whether they're stuck inside the target or where they're reflected away from the target, it's the same. They're not in the beam anymore. However, we can also have a different process. We can also see this. We can also have a photon that is hitting the target in a different direction, okay, and that is bounced into the beam. So this is reflected inside the beam, right? This could also happen. We can, in scattering, we can remove photons away from the ray, but some photons can be reflected into the ray, okay? So that is a bit of a more subtle effect. How are we going to describe this? So we need to sum over all directions. We need to include all possible direction and account for their possibly being reflected into the ray, okay? We will be describing this with an integral over all directions, which is written here in equation 22, okay? So this phenomenon uses the same scattering coefficient. So the absorption coefficient that describes scattering away from the beam or from the ray can also be used to describe the same scattering property into the ray, because it's the same phenomenon, just looking at different angles, but it's the same physical reaction. So we use the same scattering coefficient. However, we must also sum over all directions and include this probability density, which would be the phase function. So that is the scattering probability density for scattering from one direction into the other. So here, let me draw this. So that would be K. Let me draw now K prime. That's K prime, okay? So K prime is hitting this way, and that is K. So we have a probability density between K and K prime. So that would be the probability that a photon is reflected through that angle, okay? Sometimes we will model this as an isotropic probability density. So that would be just a constant, okay? Sometimes not. It depends on the phenomenon we're describing, okay? But it is just to say that it's not the same to be deflected in a small angle or to bounce back, you know? This probability density or the phase function accounts for the details of the interaction. Like for instance, suppose that the photon hits the side of the grain. Suppose that we just the photon, instead of impacting the middle of the grain, is hitting the side of the grain, for instance, that will lead to a different reflection. Okay, if it hits head on in the middle of the grain, it's likely to bounce back, whereas if it hits the side of the grain, then it's probably going to be a grazing collision, and it's not going to be deflected much, So this detail of the interaction is what we embody into this single mathematical description. We do not know exactly what the photon is going to hit. We treat it as a probability or as a random process, if you want. Okay. So in order to describe the increase of radiation along the ray, so we need to integrate over all directions. So this is what we do here, right? So I'll write again the same as equation 22, but without the integral. Okay, so we have, suppose that I'll write down here the increase in di nu due to photons that hitting, so that hit the grain or the target in direction K prime. So I'm sticking only to that case, okay? I'm only considering those photons in this drawing, right? I'm only considering those photons that are traveling towards direction K prime. So imagine we have photons hitting from this direction, K prime, and we want to know how much photons will be deflected into the beam, okay? So we'll be writing this like this, with di nu equals to the scattering coefficient, same as that the ones that remove photon from the beam. We're accounting for the same phenomenon. And then we'll include the probability density for photons to be deflected from K prime to K, okay? And of course, that is proportional to the intensities of incident photons. So that would be proportional to the incident photons. Now we have a problem here because we need to, this probability density also is a density, so we need to include here the omega prime, which is centered on K prime, okay? Because of course, the probability of being deflected from K prime to K is the probability density times the solid angle, the corresponding direction, if you want. What I'm trying to say is that the product of phi and d omega primes is a probability. Phi itself is not a probability, it's a probability density. So I need to multiply by the solid angle to get the corresponding probability. Okay. So that accounts, okay, and of course we need to also include here I'm going to add here the length interval. So let me just compare this with the true absorption with another color. Okay, so yeah, just to draw here, the true absorption, like that would be A. This would be the scattering. The true absorption is minus alpha A times I nu in this direction K times ds. So this is what we said, right? The decrease in specific intensity due to absorption can be written this way. And now we are describing the increase due to scattering into the scattering due to the increase due to scattering into the beam. Okay, and so this is what I've written here, like dis would be then the same as the absorption, but with another coefficient, which is the scattering coefficient. And so this is why we need to include alpha and ds to connect with this formula. But we also need to include another quantity, and this is what I'm trying to explain now, which is this phase function, this phi here, okay? So maybe I'll write again the scattering expression in a different way. So I'll write this again. So compare that one with di nu scattering, which is alpha s times I nu so we're talking about radiation coming from direction k prime, okay? And so this would be that would be k. So the variation of intensity in direction k is going to increase because of scattering into the ray. If we're looking at photons that are coming from k prime, the photons coming from k prime then will be scattered into the direction of propagation k, but they will be scattered with a probability that's given by this quantity here. So this describes the probability of being reflected from k prime into k, and we need to include ds. Okay, so this is a justification for using this scattering amplitude. Of course, photons can come from many directions, so we need to integrate over the incident solid angle, and this is how we get equation 22. Okay. Now, the phase function is symmetric in the sense that being scattered from k prime into k is the same as scattering from k to k prime, the same probability. Sorry, can you go back? And we normalize it. It is a probability density, so that a photon must be scattered somewhere. It's the integral of the scattering amplitude over all solid angles is 1. It must be going somewhere, okay? The full radiative transfer equation that's given in the case of a continuous medium, like interaction with dust grains or some medium with optical properties like a refractive index, which we'll be looking at shortly. In general, the scattering can be written, the radiative transfer can be written this way. The variation of I nu in the direction of propagation. Okay, so we have d I nu, this equation here. So we have d I nu over ds, which is the same as s dot nabla I nu if di nu over dt is 0. Okay, so this is steady state. Okay, if we neglect the time derivative, then this total derivative is just this. Okay, and that we can also write like this. Okay, this total variation of intensity is written like the emission, which in my summary I relate to the absorption, because we will see. Okay, so we will see that the absorption coefficient and the emission coefficient are related through the Kirchhoff formula, and we'll be looking at this very shortly. But for now, I've just added this superscript absorption to the emission coefficient, which is kind of strange. Maybe this notation is not very good. I just want to say that emission coefficient and true absorption are related by this formula, the Kirchhoff formula, which says that J nu over the absorption coefficient is B nu, the Planck function. So this is just a preview. We'll be looking at this shortly, okay? But this is why I'm using the same superscript for the emission coefficient, I'm labeling it absorption, which is a very bad idea now I think of it, just to say that I'm connecting it with the true absorption coefficient. So this part here, J nu and alpha nu, is what we described last week and that Nitya described for us today also. And this is what is then summarized in the textbook. I am now including scattering, okay? So this is the possibility that photons are removed from the direction of propagation, okay? So we have scattering is the same as absorption. We have scattering away from the direction of propagation, okay? But in the same way as we described the absorption, except that we have a different physical mechanism here, we're not truly absorbing them, we are reflecting them. So we need to label the absorption coefficient with a scar, saying that this is scattering and not true absorption. Okay, so that is easy to connect with the true absorption, but we have a more subtle phenomenon now, which is not so easy to understand and incorporate. And this is the reflection of photons into the direction of propagation. Okay, and for this, we need to sum over all incident direction. All of this, which is the last term in this equation 24, is acting like as an emissivity. It is adding to the specific intensity because of photons being deflected into the ray. We are describing this emissivity in terms of the same scattering coefficient, because being scattering away from the beam or into the beam in terms of that particular photon that's bouncing off the are the same phenomena. I mean, from the point of view of the photon target interaction, from the scattering point of view, it's exactly the same to be scattered from K to K prime, or the opposite, from K prime into K, okay? So we're using the same cross-section with this scattering cross-section. I mean, when say cross-section, I'm remembering that the scattering is can be written like this. So when we talk about the absorption coefficient, we mean the cross-section. This describes the interaction, okay? And so the effective size of the target is the cross-section, is the same if you are scattered away from the beam or into the beam. It's just a matter of angles, right? So that would depend on the scattering amplitude. And this is how we describe it. This is a way to parameterize scattering into the beam. If you look at, if you pay attention carefully, this complicated term here in equation 24 is in the end very similar to this one, except that I am accounting for the possibility that photons are coming from all directions. And I'm also accounting for that they do not have the same probability to scatter into the beam, okay? With this, I think we'll leave it here for today. I think next, Andres? Oh, we can't hear you, Andres. I think you may have a problem with. Can you hear him? No.
No.
No. No.
Dice que va a escribir en el chat.
Ah, ya. ¿Pero tú lo escuchas, Felipe?
No.
No.
No, he wrote that on chat.
Okay. Ah, yeah. Okay. Yes, it's for a continuous minimum. Okay, So what is a continuous medium? In other words, is Andres's question, I think. Okay, so what do we mean with a continuous medium? A continuous medium is one that would be described with a refractive index. It is a microscopic medium whose optical properties, whose interaction with radiation are described with a refractive index. As we will see, the refractive index has got a real part, which describes scattering, and an imaginary part, which describes absorption. Okay, so this is we will be looking at this when we look at the propagation of electromagnetic waves through a medium. But just to make a brief reply to Andres right now, we are describing like a classical medium, like a macroscopic medium, if you want, with those optical properties. And this is what we mean by a continuous medium. A continuous medium would be, it can be gas, or it can be a medium composed of dust and gas. Okay, but the point here is that we are describing the medium with an opacity coefficient, a scattering coefficient, with the parametrization that's proposed here. Okay, and is valid for a classical medium. When we will be looking at interaction with a discrete medium next week, we'll see that things are a little bit different. Okay, because and then we will not be using the same description. We'll be using the Einstein coefficients. Okay, we'll make the connection. But let's look first at what is a discrete medium next week. So let me share screen. Just for next Tuesday. So we are here next Tuesday. We'll need to jump to the Einstein coefficients. Okay, so we have till next Tuesday to prepare the section 1.4 to 1.6, please. All those three in this. I mean, I'm assuming that everyone knows about thermal radiation and the black body function. Okay, so the Planck function and the black body. We will only discuss section 1.5 if there are some issues there, something that you would like me to explain. Okay, but otherwise I'll assume that this will be covered by each of you independently. Okay, but please have a look carefully at section 1.4 and where the book introduces the optical depth and the source function, which are very important quantities. So please have a look carefully at section 1.4. Do 1.5 will just skip over, assuming that everyone knows. And then we'll also introduce section 1.6, okay? So we're not many. I've got the impression that we're only you four and myself in this class this year. So please consider that the idea is just to, I mean, since we're not very many, it's easier to discuss our problems, you know, like we're trying to learn relative processes using the standard textbook here, which is Rybicki and Lightman. And so the idea is, I mean, for you to read the textbook before we meet, and this will go very smoothly because then we just need to discuss really. In parallel, I'll be progressing with my summary as I did today. And I realize that it's more difficult to progress on my summary because I'm not explaining things very much. I'm just summarizing things, okay? But this is what I'm trying to say. Just for next Tuesday, please prepare 1.4 and 1.6, and we'll start with discussing those sections. and then I'll finish the class by going through my summary. Okay. So if it's if
Professor,
Pratyush, hello.
yeah, a couple of quick questions regarding the equation that you wrote for continuous medium. So suppose if the radiation is coming from K prime direction and going into K direction, so there we use probability function. But if when it's going from K direction to, let's say, K prime direction or K double prime direction, then why we are not taking into consideration some probability? Because if it's getting reflected into K prime direction, then again there is not uniform probability in all directions when it's getting reflected. So is it just the case that it's going away from K direction, so we don't care? That's why it's just an, we're considering as pure absorption, or
Now that's a very
what
good.
is the subtlety there?
Yeah, that's a very good question, Pratyush. Maybe I should have expanded on this. Okay, so we're looking at scattering away from K. So that would be, that's the ray. Okay, and so really what we should be writing is something like this. So what I mean is the scattering amplitude, okay, times the integral over all solid angles. So we are being scattering from K to K prime. So this is what you mean, right? We are scattering from K, where we're looking, photons are going in direction K and scattered into K prime, okay?
Correct.
Times I nu in K times ds, okay? So this is the same formula as scattered into the beam, but away from the beam.
Yes.
Yes? Okay.
Yes.
So if you pay attention, this integral is taken over omega prime. So this is an integral over K prime. But in the integrand, I have this incident specific intensity along the ray K, which does not depend on the integration variable here. So this goes out of the integral, okay? I can write it like this.
Okay. And then that will become 1. Okay.
Exactly. And then this one is 1 because the phase function is normalized by definition, okay? Okay. So in the end, we have that absorption, scattering away from the direction of propagation is, sorry, that was not necessary, is just that term. And that's why it looks different from that other one.
And the second question that I was asking was whether this equation is true for inelastic scattering as well.
Misheard. Can you repeat the last part?
Is the equation 24 is also valid for inelastic scattering as well?
Now that is a more difficult question, Pratyush.
Maybe next.
Yes, inelastic scattering would be like a combination of absorption, where we have radiation being absorbed by the target, and a reflection. So we are splitting inelastic scattering into an absorption part and a scattering part, okay? So what I'm trying to say here, Pratyush, is that we are proposing a physical model where we have, on the one hand, real absorption, the photon disappears. And on the other hand, we have elastic scattering, where the photon is perfectly reflected. But as you well point out, in real life, it's in between, right? Yes. And so we have a combination of both. When we will be looking at the propagation of radiation into a medium, we'll see that the same interaction between an electromagnetic wave and the medium will lead to the two phenomenon. That will lead to absorption and elastic scattering, okay? And so in the end, the inelastic scattering is the general case where we have the combination of both, okay? And so I invite you to keep this question in mind until we look at the propagation of an electromagnetic wave into a dielectric medium, which has got a refractive index and where we'll be looking at the scattering as well in there. Okay?
Okay. Thank you.
Good. So I apologize for extending the lecture a bit too long. I started late, but thank you very much for participating today. We're not very many, but we're interested and we will learn radiative transfer, I'm sure, by the end of the semester. See you next week. Ciao.